Hello, everyone. Yeah, thank you all so much for being here. I'm really excited to bring this presentation to you all today. I'm going to begin as we usually do with a land acknowledgement, where I'm sitting here in Hood River along the Columbia River Gorge is the traditional territory of the Wasco and Wishram, Warm Springs, Yakima, and other cultures that have been a part of this ecosystem and managed its resources sustainably since time immemorial. If you don't know on whose traditional territory you are on, there's a very helpful link in the chat. Yeah, I would definitely suggest learning about that. We do these land acknowledgements to both recognize on whose traditional territory we are on, but also to recognize the, enduring role of those peoples and cultures in, the current and future management of these resources. So yeah, with that, I'll introduce Columbia Riverkeeper. For those of you who don't know, um, we are a nonprofit organization that works up and down the Columbia River to protect water quality, clean up toxic sites, promote a stable climate so that everyone in the Columbia Basin and beyond has the benefits of a healthy, clean river that we all can enjoy. My name is Miles Johnson. I'm the legal director for Columbia Riverkeeper. I lead our work on Snake River dam removal and other efforts to restore healthy and abundant fisheries. With me today, I'm very lucky to introduce Dr. John Harrison. Dr. Harrison is the Edward R. Meyer Distinguished Professor of Environmental Science at Washington State University's School of the Environment. His research is primarily focused on the sources, transport, transformations, fate, and impacts of nutrients and carbon as these elements move downstream from the uplands to the sea. He has a bachelor's in biology from Brown University and a Ph.D. in geological and environmental sciences from Stanford. As we go into this presentation, we're hoping to hold time for Q&A. Um, I ask that people use the Q&A feature in Zoom. I'll be looking at that throughout. I can't promise that I will answer absolutely every question, but I'll attempt to do my best to get my arms around the important topics and, see what bubbles up. Bad methane pun. Um, by the end, and hopefully we can, cover some of the big areas that people have questions on. Um, so yeah, before we get to Dr. Harrison's presentation, I want to do just a tiny bit of a table setting and just a little bit of advocacy before we delve into the science. What you're looking at here is a picture of the lower Snake River last summer. And the big green blob in the middle of that picture is a large bloom of algae. It happens to be toxic algae. That's probably a subject for an entirely different webinar. But I think a lot of people know, and maybe intuitively, just from spending time on the water, that where we see big algae blooms is oftentimes in warm, stagnant waters that have a lot of nutrients coming into them. And as I think you'll hear and understand as Professor Harrison gets going, those are some of the same conditions that we see producing in reservoirs higher levels of methane emissions. And I say this, so that when you go away from here and you hear people say that our hydro system and the lower Snake River dams are, producing energy that's carbon free and not contributing to global warming, because those reservoirs are cold and clear and don't have the kind of conditions that result in methane emissions. Yeah, just think about this slide. Think about this presentation that you're about to hear. Yeah, just think about that. With that, I'm very happy to hand off to Dr. Harrison. And I think, yeah, what you're about to hear is really important and really interesting. So thank you all for being with us, and especially thank you, John, for being here with us today.
Great, thanks, Miles. That's a very nice introduction and puts this issue in the context of the Pacific Northwest very nicely. Let's see. I thought I'd start here by sharing a short video that shows the conditions that first got me interested in the issue that I'm going to talk about today. This is from a trip that we took down to Foster Reservoir in Oregon a number of years ago, where the reservoir operators were drawing down water level, and we would see bubbles rising to the surface, just like bubbles rising to the surface of a cup of Coca-Cola when you open and pour it into a glass. And this really visible process was something that got me and my group interested in whether this could be an important pathway for methane emission to the atmosphere globally, where, when, and why it's significant. And I'm going to talk to you a little bit about our work on those topics today. Before I get into that, though, I want to give a little bit of background to make sure everybody's on the same page here, because folks are coming from a number of different backgrounds. So some context. There are a lot of dams globally. By a conservative estimate, well over 1 million. By some estimates, somewhere around 16 million or 16 million dams globally, most of which have been constructed over the last century and a half. In the US, we have more than 80,000 large dams, according to the Corps of Engineers. And the number of dams on the landscape is globally, although there are areas where dams are coming out. These dams are generally built because they have benefits to the societies that they serve and the watersheds that they're located in. And these benefits include things like water for irrigation and flood control, enhanced navigation of river systems, and of course, provision of hydropower. In our region, about half of our electricity comes from hydropower. So dams are an important part of the Pacific Northwest. Dams and reservoirs are also used for recreation, drinking water, and to control mine pollution and mitigate that to some degree. But of course, this group is, I'm sure, well aware of the fact that dams also are associated with a number of important negative consequences, including displacement of peoples and the fragmentation of river habitats, the massive scale alteration of hydrographs, both regionally and globally. By building dams, humans have altered the flow of about 3/4 of the world's long rivers. We've increased residence times of freshwater on land by about a factor of 3, and increased the amount of freshwater sitting up on land by about a factor of 7. And from a chemical perspective, something that my work focuses on, dams are really important at controlling the flow of nutrients and carbon across the landscape. They retain a lot of nitrogen and phosphorus, about 10 times more per unit area than natural lakes, and prevent that nitrogen, phosphorus, and silica from entering downstream ecosystems and eventually the coast. And the topic that I'm going to talk about today is the fact that reservoirs emit a lot of methane. They're places where you can think of them as chimneys for methane to the atmosphere. Just how much? Well, it's uncertain, but it's well established that it's a lot globally. This is a pie chart showing the relative contribution of various human sources of methane to the atmosphere. This wedge here in the lower left in red is an estimate of the contribution that reservoirs make to global emissions of methane. You can see it's smaller than some of the other major sources you might think of, like fossil fuel, mining and leaks associated with natural gas wells, or domestic ruminants, cow emissions, and so forth. But it's on the same order of magnitude as things like rice cultivation or biomass burning, or even at its upper end, landfills as sources of methane to the atmosphere. It's also not particularly well understood or constrained as a source. So what I'm going to talk about today is some of our efforts to understand the size of this wedge and where methane emissions from reservoirs are occurring globally, and how they're changing over time, and what controls them, and maybe even what we might do about these emissions. Okay, before I get
Sorry.
into why should you care about methane emissions and methane emissions from reservoirs in particular? Well, methane is second only to CO2 as a potent greenhouse gas in our atmosphere. It's responsible for roughly a third of human-caused warming. Concentrations of methane are rising rapidly in the atmosphere. Over the last century and a half, we've seen about a tripling of methane concentrations, and after a brief pause in the early 2000s, methane concentrations in the atmosphere are again on the rise. And methane is particularly important as a greenhouse gas because it's super potent on a per mass or per molecule basis relative to CO2. It doesn't last very long in the atmosphere, but when it's in the atmosphere, it does a lot to hold heat in the atmosphere. In fact, on a per mass basis, it's about 80 times more effective than CO2 at holding heat in the atmosphere. Like I said, it's especially potent over short time periods, and it's because it's really potent over short time periods, it's really important in allowing us to meet our short-term goals to keep global warming within what's considered a safe operating space for humanity. And because of this, the Biden administration committed to reducing U.S. methane emissions by 30% by 2030 in Glasgow a few years ago. And this is a major effort that's going on, focused primarily on leakage from the fossil fuel infrastructure in our country. But if we can reduce methane from other sources, that helps as well. And reservoirs, I hope you'll understand by the end of this talk, are a potential piece of that methane reduction portfolio. So a little bit more background. Why do reservoirs cause methane emissions to the atmosphere? In an undammed watershed, you might expect that water and organic matter would flow from uplands through rivers and streams down to the coast, and along the way, much of the water that organic matter is flowing through is well oxygenated, and when it reaches the coast, it's exposed to the salt in seawater, and oxygen and sulfate, an important component of the salt in seawater, both facilitate the transformation of methane, a really potent greenhouse gas, to CO2, still a greenhouse gas, but a less potent greenhouse gas than methane. And when you add a dam into a watershed, you hold water in place, create stagnant and slow-moving conditions, allowing for water stratification because of density differences to occur. And that organic carbon, in the absence of oxygen and sulfate in seawater, is emitted to the atmosphere as methane. Much less of that organic carbon is ultimately transformed into CO2 and lost to the atmosphere or dissolved in water. Okay. So that's a little bit about why dams create net methane emissions to the atmosphere. within dams, methane is produced primarily in low oxygen sediments, and it has to get to the atmosphere through the overlying water somehow. And how it does that is really important because when methane diffuses out of sediments, it is released into the overlying water relatively slowly, and the organisms that use methane as an energy source consume it and prevent that methane from reaching the atmosphere pretty efficiently. But when methane bubbles out of sediments, or when it's put into contact rapidly with the atmosphere by flowing through turbines and being released downstream, methane can be efficiently released to the atmosphere, resulting in an overall increase in methane emissions. Because of that, how water is released through dams, and also whether water levels are kept constant or fluctuate, because that can affect how much bubbling occurs. It's a little bit of foreshadowing. All this can affect how much methane is released to the atmosphere. And so number of years ago, nobody thought of, I mean, as Miles referenced, people have for a long time thought of hydropower and dams as a carbon neutral or climate neutral source of energy. But there was a seminal paper in 2000 that suggested that reservoirs globally could be a significant source of methane, CO2, and another greenhouse gas, nitrous oxide, to the atmosphere. And since that paper kicked off this discussion, there's been a burst of activity where people have gone out to lakes and reservoirs and tried to measure greenhouse gas fluxes. And they do this in a number of ways. One common way is to put these chambers, these flux chambers, out on water surfaces, and then measure how fast methane and CO2 accumulate in these chambers. And these are just examples of ones that we use out on Bonneville Reservoir here for just as an example. So there has been a lot of work recently, and in 2016, my former PhD student, Bridget Deemer, led a synthesis effort with a number of people that do this kind of work to understand and revisit a global estimate of methane and CO2 and nitrous oxide emissions to the atmosphere. And what that now quite influential paper showed was that in the more than 200 reservoirs that had been studied at that point, methane fluxes were significant and positive from reservoir surfaces to the atmosphere. This study also suggested that reservoirs emit more methane on a per area basis than natural lakes. And collectively, our estimate was that reservoirs produce about 1.3% of total global human source global greenhouse gas warming potential, mostly as methane, about 75% as methane. Doesn't sound like a whole lot until you start to compare that with national emissions estimates. And it turns out this was about the same as what Canada emitted the year that this study came out, and they were the 7th largest national emitter globally. Another aspect of this study was it was the first one to include bubbling into global estimates of methane emissions, and that increased our per area estimates of emissions by about 25%. And this got picked up by a number of influential megaphones and publicized, and led to our group and others being invited by the Intergovernmental Panel on Climate Change to develop a first ever method for countries to estimate greenhouse gas emissions from what they call flooded lands, which is mostly reservoirs globally. And we did that, and this was accepted by the IPCC as their method in 2019, and now countries are implementing the recommended method that we came up with, which is pretty exciting, including EPA, which has developed its first nationwide estimates of greenhouse gas emissions from reservoirs. And the method that they use, however, it leaves some room for improvement. Because every country in the world has to be able to implement a method that's recommended by the IPCC, these methods are necessarily quite simple, and they gloss over many aspects of emissions that might be important to include. And in this case, the method that was recommended accounted for bubbling and diffusive losses of methane to the atmosphere, as well as methane degassing downstream. But the way that it did that was quite simplistic. I'll get to that in a second. It also accounted for CO2 diffusion from the surface of reservoirs. And it did this by simply multiplying the area of a reservoir and how nutrient rich that reservoir was by an emission factor, a per area rate of methane emission to the atmosphere that was dependent on the climate in which a reservoir occurs. And it's a reasonable first cut, but there's a lot of room for improvement there. The downstream emissions were simply calculated as 9% of the total emissions from the reservoir surface, which was an average globally, and CO2 emissions were assumed to be zero if a reservoir was over 20 years old, or the average of the total amount of organic matter that was flooded when a reservoir was constructed, divided by 20 years. And I imagine that folks listening to this are thinking, well, maybe that's an okay way to start, but I bet people can do better who know something about reservoirs. And that's what we thought too. Oh, and also we in the tier one method recommended that people take individual reservoir emissions and sum them up by country, and that's your national number. But so we thought we could do better. And so a number of years ago now, 2019, I went and did a sabbatical with colleagues at the University of Quebec in Montreal who had developed this reservoir model to estimate emissions of methane and CO2 from individual reservoirs. We wanted to see if we could apply this at a global scale and refine it so that it was applicable at a global scale. So we did that and incorporated new flux measurements, and we developed a model that could be applied for an individual year instead of an average of multiple years. We developed a model that could estimate diffusive and bubble fluxes separately, as well as downstream degassing fluxes. And importantly, we corrected for a problem that has been recognized now with the tier one IPCC method, which is that it systematically underestimates methane fluxes from reservoirs. And so this model took reservoir characteristics and related them to measured fluxes. And it turned out that things like reservoir age and reservoir trophic status and reservoir temperature all correlated with reservoir greenhouse gases. And so we were able to develop a model and apply it and test it. Before we applied it, we wanted to test it. So this is what a comparison of measurements on the x-axis and model predicted fluxes based on this modeling exercise look like. This is a log-log plot. So if you have to be careful in applying this model to any individual reservoir, because what looks like a small difference between predicted and measured fluxes here could be quite large. If the model were perfect, everything would line up on this one-to-one line. And you can see it doesn't, but the models do a whole lot better than just taking a mean of reservoir emissions and applying that globally. And so we were able to take this model or set of models and apply it to develop the first ever global picture of reservoir emissions of methane and CO2 to the atmosphere. And that's what's shown here. Here, the colors represent per area fluxes on top and total fluxes of methane and CO2 represented as CO2 equivalents from all of the emissions pathways together in the maps and then separated by emissions pathways by latitude here on the right. The hot colors represent high flux systems, and the cold colors represent low flux systems. You can see that some of the highest per area fluxes occur in the tropics, but there are high flux areas in the temperate zone as well. So this isn't simply a tropical problem as it's often portrayed. And there is an interesting latitudinal pattern where CO2 or carbon dioxide fluxes tend to dominate emissions from reservoirs at high latitudes, and methane fluxes, and in particular, methane fluxes due to bubbling and downstream degassing tend to dominate in low latitudes in the tropics and subtropics. It's worth pointing out that most measurements that we have are of diffusion. There are comparatively few measurements of bubbling or degassing. So most of the flux here is attributable to flux pathways that are not well measured or well understood, but likely to be quite large based on the measurements that we do have. When you look at global totals, the way this model happens to be constructed, we estimate that about 3/4 of reservoir emissions are occurring between in low latitudes in the tropics. However, as you'll see in a minute, some of our measurements here in the Pacific Northwest cast some doubt on whether this is a reasonable representation of reality. And our global totals add up to similar numbers that people have gotten using other simpler techniques. And so that lent us some confidence in this approach. And as I showed in the beginning, these numbers might not mean much to you without context. To give some of that context, these fluxes of total emissions are similar to rice cultivation and biomass burning, some of the major human sources of methane that I mentioned earlier in the talk. As I also mentioned, you can use this model to look at how greenhouse gas emissions from reservoirs are changing through time. And part of that is how reservoir area is changing through time. So you need to know both what the per area emissions are from reservoirs and what the total reservoir area is. And so that increase in reservoir area is what I'm showing here. And you can see that although a lot has been made of a potential boom in hydropower in coming years, most of reservoir construction actually happened between 1960 and about 1990. We're seeing a little bit of a bump now, but it's not living up to some of the predictions that have been made earlier in the 2000s, perhaps because other renewables are actually more cost effective than hydropower is to build. But there is an ongoing increase. Contrary to what we thought was going on, most of that increase in area is actually happening in the temperate zone, not the developing tropics and subtropics, as some people have postulated. And we can take this information about reservoir construction and combine it with our model of reservoir emissions to understand how emissions from reservoirs are changing over time. And once again, this is similar in that the colors represent different latitude bands. The totals reflect reservoir carbon gas emissions over time. And this was surprising to us in that we expected with increasing reservoir surface areas, we'd also see increasing trends in reservoir greenhouse gas emissions, but that doesn't appear to be the case. And in fact, what our results suggest is that sometime in the mid-80s, we reached peak reservoir greenhouse gas uh, emissions in the form of carbon. Um, and that was interesting and surprising to us, but it's only part of the story. And it's due to the fact that reservoirs emit a lot of carbon dioxide early after being flooded. But then as organic matter that's been flooded is um, decomposed, the CO2, the carbon dioxide emissions decrease. But as reservoirs age, methane emissions continue to take place. So as reservoirs globally are aging, a greater fraction of the total greenhouse gas that's emitted from reservoirs is occurring as methane, this super potent greenhouse gas. And what that means for the climate impact of reservoirs on the atmosphere is that radiative forcing due to reservoirs, it has increased greatly through time and is going to continue to increase as methane continues to be emitted from reservoirs. And what's shown here is a calculation, and the result of a calculation that estimates reservoir radiative forcing, so the total net impact of the gases emitted by reservoirs on global climate over time. And this is pieced out so that you can see the individual gases and the flux pathways, as well as the totals. And the take home here is that the radiative effect of reservoir emissions is likely to continue to increase well into the 21st century. And we estimate that by 2060, it will account for somewhere between 1% and 3% of total human radiative forcing. So 1% to 3% of the total impact of humans on climate. And it'll account for somewhere between 6% and 8% of the effect on climate due to human methane emissions. And it was surprising to us how big component of radiative forcing these systems seem to be. Together, methane flux is accounted for almost 90%, 88% of reservoir-associated radiative forcing at the turn of the century, and even more in subsequent years. How big are these fluxes relative to other sources? Well, for methane, it looks like reservoirs constitute the fourth largest global source of methane to the atmosphere due to human activities, which was also surprising to us. And when you add CO2 into the mix and look at total impact of reservoirs on the climate, they come in somewhere around sixth or seventh, comparable to sources from global shipping enterprises or global air traffic. So where does that leave us? Let's see how we're doing. Global reservoir greenhouse gas emissions, and especially methane emissions, are clearly substantial, and we've made some progress in understanding where they occur. Global peak of reservoir carbon gas emissions is likely behind us based on this modeling exercise. But the climate impacts of reservoir emissions still lie ahead of us. And this is due to continued increases in methane emissions from reservoirs over time. Most global reservoir methane occurs via really uncertain and highly management sensitive pathways by bubbling and downstream degassing. And so there's quite a bit of work to do to better understand those pathways. And overall, we've made some progress here, but simply in recognizing this as an issue, we've made some progress, but we've made some progress in understanding how it works too. But there's still quite a bit of work to do. For example, the GRES model that I've been talking about doesn't do a great job representing management sensitive levers. It doesn't say anything about what we might do to change how we manage reservoirs and rivers to reduce how much greenhouse gas they emit. And this is important because research into these potential changes has has the potential to tell us how to do some clever things to reduce methane and CO2 emissions to the atmosphere from these systems. For example, some of the work that we've done in Pacific Northwest reservoirs shows pretty clearly that there's at least a transient increase in methane bubbling that occurs when you draw reservoirs down. These are methane bubbling fluxes from 5 reservoirs that we studied a number of years ago now, showing that when you compare pre-reservoir drawdown and post-reservoir drawdown across a range of different reservoir types, you see a major, almost well, more than tenfold increase in methane bubbling in each case. Now, the total impact of not drawing reservoirs down wouldn't necessarily be to decrease reservoir methane emissions by tenfold, because the impact of these drawdowns is mostly to increase the efficiency with which methane is transferred to the atmosphere, not the total amount of methane that's produced in the system. But this might be a way to reduce methane emissions to the atmosphere by thinking more carefully about when and how much we draw reservoirs down. Also, in this study, we had a direct comparison between a reservoir that was managed for constant water levels and one that was managed to do hydropeaking. So it went up and down daily. And we saw about a threefold higher methane emissions in the reservoir that was going up and down than the one that was managed for constant water levels. There's also a pretty clear and consistent relationship, both in our Northwest reservoir study and globally, between how green reservoirs are. So that's not how environmental they are, but how much chlorophyll there is in the water, and how much methane bubbles out of them. As Miles referred to in his intro with the picture of the Snake River, the chlorophyll conditions, or how much organic matter is being made and buried in sediments, can affect how much methane is ultimately emitted to the atmosphere. And in fact, when you look at reservoirs in the Pacific Northwest that are not carbon rich, that are what we call oligotrophic, clear water, cold systems generally, they do tend to have fairly low methane emissions when placed in a global context relative to reservoirs in the tropics and reservoirs in temperate and boreal regions. But when you look at mesotrophic and oligotrophic systems that we've studied, including some of the iconic systems on the Columbia River that we're in the process of studying right now. So these numbers that are grayed out are provisional because we're still working up the data. But these fluxes are comparable to fluxes from tropical reservoirs, and in some cases, in the really enriched systems, they can blow tropical systems out of the water with respect to how much methane they're producing and emitting to the atmosphere. So to follow up on some of these things and understand them better, I'm working with a transdisciplinary group of colleagues here at Washington State University with National Science Foundation grant money to understand how reservoir water level management and residence time management affect a number of different ecosystem response variables, including greenhouse gas emissions. And this project has a significant stakeholder engagement piece. So if there are people on the call that are particularly gung-ho about this stuff and want to get involved, I encourage you to contact me about it. The goals of this project are to provide useful guidance to communities seeking to enhance environmental sustainability of reservoir systems, and also do that while providing novel insight into how these systems work. We also have a brand new and exciting project on the Klamath River, where one of the, if not the largest river restoration project ever is in progress right now. And what we're trying to understand there is how reservoir drawdown and dam removal affect greenhouse gas emissions to the atmosphere by looking at pre-drawdown and post-drawdown emissions from these systems and also comparing gas fluxes in exposed sediments with um, emissions from a reservoir that's remaining in place. And this is a project that's brand new and provides an opportunity to understand whether the process of reservoir construction and greenhouse gas emission increases is reversible, which I think is cool. So stay tuned for results of that. We also want to explore how nutrient enrichment and greenhouse gas emissions interact at the global scale. The current models don't do this very well, so that's something we're working on. And I have a kind of interesting and fun little collaboration with an engineer who is interested in seeing whether we can take the methane that's being produced and emitted from reservoir systems and reclaim some of it and turn it into things that might be commercially viable. So thank you for listening. I think I'll open it up for questions if that works. With thanks to colleagues and collaborators here.
Well, thank you so much, John. Yeah, that was great. Just a quick plug here. Yeah, if you appreciate this kind of content and the work that Columbia Riverkeeper does, you can become a member and support our work. We're blessed to have thousands of people around the region who are giving what they can and being a part of a movement to protect and restore the Columbia Riverkeeper. Trust me, there's no amount of support that's insignificant. So yeah, appreciate you considering it. If you already support Columbia Riverkeeper, thank you so much for powering this work. There's going to be some resources in the chat if you want to learn more about the issue of methane emissions from reservoirs. Yeah, looking forward to doing some Q&A here. I think, thank you to folks who put questions in the Q&A feature. I don't think everyone can, I'm not sure if everyone on the Zoom can read those, so I'll go through and read some of them out. Yeah. First one here is kind of about should greenhouse gas emissions from reservoirs be considered additive to an undammed river system? And I take that to mean like, are these, are these emissions something that would happen anyway in a naturally flowing river, or is this something that is like happening because of the way that we've constrained rivers for hydropower or flood control or whatever?
I think it's a great question, and the answer in my mind is that because of what I was saying early on in the talk, that reservoirs create conditions for methane production and emission that would not occur otherwise, they can be considered an additional source of methane to the atmosphere. With CO2, the story is a little different. And there, aside, what our consensus view in the IPCC group was that unless you're thinking about the organic matter that's being decomposed and emitted to the atmosphere as CO2 because of the flooding, the reservoirs don't create a net source of CO2 to the atmosphere because the CO2 that's being emitted from a reservoir surface is really CO2 that would be emitted downstream anyway. And much of it, in fact, is coming from terrestrial sources, so from forest soils and being washed into the reservoir and then being emitted to the atmosphere there. So there's an important distinction between methane and CO2 there. that help?
Yeah, that's great, I think. A question about like the interaction between drawdown and methane release and dam removal. What kind of like what should we be taking away from this? Does it mean that would it be preferable to limit operations of reservoirs, um, like limit drawdowns or limit the kind of big fluctuations in reservoirs from a methane emission standpoint? And kind of building on that, like if you remove if you remove a dam and get rid of the reservoir entirely, are are you just dumping so much methane into the atmosphere that like that's actually worse than, the ongoing um, methane emissions that would occur from having that reservoir um, on the landscape? Kind of a two-part question, but maybe you could speak to that.
Uh, sure. The short answer is we don't know, and that's why we're doing the work that we're doing to figure that out. And our work on the Klamath is a project that's aimed at gaining insight into exactly that set of questions. Um, so I hate to say stay tuned. We'll be able to speak to that better in a few years. But I think as a community, that's something that we're working on and trying to understand better. What would be really useful there is if we could work with reservoir operators to do prospective experiments where we manipulate reservoir drawdowns and then look at the greenhouse gas emissions response. Turns out that's a hard thing to do because reservoir operations are, at least they have been pretty strictly constrained by congressional acts that tell reservoir operators how they can manage water. There is apparently an increasing amount of flexibility there. So we're optimistic that we can do some fun experiments. But thanks for the question, and you can imagine that it could go either way, right? The carbon that's locked up in sediments that's been deposited there for tens or hundreds of years could be stored or it could be released when a reservoir is drawn down. And how it's released, whether it's released as CO2 or methane, how fast it's released, all these things will affect the answer to your question. So, got to do the work.
Um, Good question about whether like globally methane from reservoirs is increasing or decreasing. It looked like, some of those charts, it was it had carbon emissions from reservoirs had kind of peaked early and were declining, but in other ways were expanding. Like how can we think about that in the big picture? Is this a problem that's getting worse or getting better?
Sure, yeah. I might throw that slide back up because I realize it probably went by fast. And I could have spent a little more time explaining it. But I think this is the slide that you're interested in. Can you see my, oh, um,
I can, all right, there we
can
go.
you see my screen now?
We've got it.
Okay. So I think this is the slide you're referring to. And here in purple, these are the CO2, the carbon dioxide emissions, and methane emissions are in red, orange, and yellow here. The different pathways are represented by the different colors for methane. And so overall, although the total carbon emitted from reservoirs as gas is projected to decrease over time, the amount of methane coming out of reservoir systems globally, collectively, is rising. And it turns out that's more important in terms of the net impact on climate than the overall decrease in carbon-based gases, because methane is so much more potent than CO2 as a greenhouse agent. Does that work?
Yeah, I think that was really helpful. Got some questions about like measurements of greenhouse gas emissions from dams and reservoirs in the Northwest. Yeah, could you just kind of maybe a little perspective on the use of these tools to like these modeling tools to assess like individual reservoir emissions, whether they are, helpful, how should we be thinking about them? What would it mean to actually study um, emissions from individual reservoirs? Um, and, I think a lot of people want to know, like, how can we feed this back into the, like, can this feed back into the policy decisions that, our region is faced with?
Okay. I'll start with the
You,
measurements there.
you don't have to hit the last one if you don't want to, but
Well, no. I mean, I can speak to it, but yeah, it's going to be this is going to require some discussion and work kind of answer. So measurements, I there are a number of different ways to measure greenhouse gas emissions from reservoirs, and not very many of them have been applied to Pacific Northwest reservoirs. Um, and as I showed you, I hope one of the take-home messages from that slide showing the comparison between measurements and modeled or sort of estimates of greenhouse gas emissions from first principles is that there's no substitute for getting out there and measuring greenhouse gas fluxes if you really want to understand how much greenhouse gas a reservoir is producing and emitting to the atmosphere. And that's challenging because there's a lot of spatial and temporal variability to account for. That said, because so little has been done on Pacific Northwest reservoirs, there's an opportunity to greatly increase our understanding of how these systems are acting as sources of methane to the atmosphere. And we're doing some of that, but there's certainly room for agencies to do this on a longer term, more and consistent basis. I think that would be fantastic. And in terms of the nuts and bolts, we use a number of different approaches all at the same time to try to hit the problem from different angles and therefore have more confidence in our estimates as a result. So we'll go out and measure, we'll take water samples and then measure supersaturation of methane and CO2 back in the lab. We have these flux chambers that measure the emission, the accumulation of methane and CO2 just above the water surface. We don't use techniques like eddy flux and eddy correlation, but there are people that are doing that. It's more expensive, labor and data intensive, but gives you really fine scale temporal and spatial information about gas fluxes. And it could be employed on some of the dams around the Pacific Northwest. That'd be really cool, I think. That's so those are some of the techniques that people use to measure these fluxes. How do we get this information used? Well, I mean, I think talks like this are a step in the right direction. I also think talking with the communities of practice that make decisions about reservoir operations is really important. That's something that we're making progress with through the National Science Foundation project I mentioned, but there are a lot of other opportunities to, I mean, that's just kind of a drop in the bucket, I think, in terms of really getting this question or this set of issues out there and being utilized and discussed. I and I think there's more science that has to be done to really understand how effective management changes might be in reducing greenhouse gas emissions to the atmosphere. So once again, a lot of work to do, I guess. And if you're interested in making progress on it, please feel free to get in touch.
Thanks so much, John. I think that's probably a pretty good place to wrap. You know, I really appreciate all your whole career of work on this to, even begin getting our arms around this issue, and, certainly all your time today to, help explain it to folks who, I think a lot of us here in Northwest are, you know, we live in kind of this uneasy existence to dams where we know that they, have had tremendous impacts on our freshwater ecosystems and fisheries and the people who depend on them, but we think about them as also, allowing us to avoid heavy dependence on, on fossil fuels in the way that some regions of the country have done. And yeah, as we work towards, the goals of carbon neutrality and limiting change to 1.5 degrees, or, whatever measure you want to point to as, what we need to do. Yeah, this is just obviously a tremendously important and not nearly well enough understood part of that puzzle. So yeah, I think I'll close there, but yeah, just want to express a lot of gratitude for your time, and thank you to everyone who, yeah, tuned in today. I hope you found it interesting and helpful, thought-provoking. I know that I did. And yeah, look forward to talking to everyone in the near future. Yeah, feel free to contact me as well with questions and follow-up.
All right. Thanks, Miles. Appreciate the opportunity.
My pleasure.
Take care.